Have you ever stopped to wonder what a simple little gas lighter could possibly have in common with a super complex medical ultrasound machine? Well, today we're going to pull back the curtain on a hidden bit of science that connects all sorts of everyday objects in a way that honestly might just change how you look at the world.
Okay, so take a look at this collection of things. You've got a gas lighter, a quartz watch, an ultrasound probe, even a microphone. I mean, on the surface, they've got absolutely nothing to do with each other, right? But they all share one incredible secret, a remarkable physical principle that makes every single one of them work. Any guesses what that could be? If you guessed the piezoelectric effect, you are spot on. Now, I know it sounds super complicated, but it's actually a beautifully simple idea that connects the physical world of pressure and squeezing with the invisible world of electricity. It's the magic ingredient they all share. So, what exactly is this effect? Let's dive into what I like to call the magic of squeezing, to really understand how this all works.
You know, the name itself is actually a huge clue. Piezo comes from the Greek word piezein, which literally means to press or to squeeze. It was discovered way back in 1880 by the brothers Pierre and Jacques Curie, and it's just this, the amazing ability of certain materials to generate electricity when you put them under some kind of physical stress.
Here's a great way to picture this. Just think about a sponge. When you squeeze it, right, you're applying mechanical stress. And what happens? Water comes out. Well, that water is kind of like the electric charge being generated in these materials. It's a really simple way to visualize this cool physical to electrical conversion. But wait, the magic doesn't stop there. This is actually a two-way street. So the direct effect is what we've been talking about. You squeeze the material and you get a voltage. That's perfect for things like sensors. But then there's the converse effect, which does the exact opposite. You apply electricity to the material and it physically changes shape. This makes it an actuator, something that can create movement. Just incredible. Two amazing properties from one single effect. Now, to really get this, we need to zoom in. I mean, way in, down to the atomic level. So let's look at the anatomy of this whole effect using one of nature's best examples, quartz. So the whole secret is hidden in its atomic structure. Quartz, or silicon dioxide if you want to be formal, has this hexagonal crystal lattice. And the most important part, the crucial detail, is that it's asymmetrical. It doesn't have a perfect center of symmetry. Now, this isn't some kind of flaw. It is the absolute key to its power. That little bit of asymmetry is everything. Okay, so inside that structure, you've got silicon and oxygen atoms. Oxygen is a bit more, let's say, grabby with its electrons. It's more electronegative, so it pulls the electrons a little closer to it. This creates this tiny, permanent separation of charge, a positive end and a negative end. That's what we call a dipole. You can almost think of it like a microscopic magnet. Now, when the quartz is just sitting there, totally unstressed, all those little dipoles are arranged in this perfect, beautiful balance. All the positive and negative charges just cancel each other out. The net charge is zero. Everything is perfectly in equilibrium, nice and quiet. But then, you apply pressure. You squeeze that crystal, and boom, that perfect balance is totally broken. The structure deforms, the charges get knocked out of alignment, and all of a sudden, the positive and negative centers don't cancel out anymore. This creates a net charge separation, and that gives you a measurable voltage. And that voltage, that is exactly what's happening inside that gas lighter. The click you hear, that's a tiny little hammer striking a piezoelectric crystal, creating a jolt of high voltage, the spark, that ignites the gas. It's simple, it's elegant, it's pure physics in action. Quartz is awesome, no doubt, but it's a rigid, natural crystal. It's basically a rock. What if we need something flexible? Well, this brings us to a modern synthetic twist on the very same principle, a polymer called PVDF. So how do these two stack up? Well, quartz is natural and rigid, and it's prized for its stability. That's exactly why it's in your watch, keeping perfect time. PVDF, on the other hand, is a synthetic polymer. It's flexible, it's lightweight, and it actually has a much stronger piezoelectric response. So you can see they're basically different tools for different jobs. But there's a little catch with PVDF. Unlike quartz, it isn't naturally piezoelectric right out of the box. Its molecules can be arranged in a few different ways, or phases. And in its normal state, the charges just cancel out, kind of like the quartz at rest. To unlock its power, you have to transform it into a special beta phase, where all its molecular chains align just perfectly. So how do they do that?
It's through a really cool process called polling. First, they take the PVDF film and mechanically stretch it out. Then, while it's stretched, they zap it with a really strong electric field. This 1-2 punch forces the polymer chains to snap into that all-important beta phase, and it locks their dipoles into perfect alignment. It's basically like activating the material's superpower.
And because this process works on a thin, flexible film, PVDF is the absolute ideal material for things that need to bend and move. We're talking wearable sensors, smart fabrics, and all sorts of other next-generation technologies. So, we started with a humble little lighter, but the applications for materials like quartz and PVDF are, well, they're truly mind-boggling, and they are already shaping our future in ways you might not even realize.
I mean, think about it. In medicine, they're the heart of ultrasound probes and wearable pulse monitors. In your car, they're in tire pressure sensors. They're in the microphone you talk into, in high-tech earthquake monitors. And they're even in futuristic ideas that are becoming real, like smart floors that generate electricity from nothing more than our footsteps. This stuff is everywhere.
Okay, we've covered a lot, from atomic structures all the way to smart floors. So let's just boil it all down. What are the key things you really need to remember here?
First, piezoelectric materials are the ultimate bridge between physical force and electricity. Second, nature gives us these super stable options like quartz, which are perfect for precision devices like watches. Third, modern science is giving us flexible polymers like PVDF, which are totally blowing the doors open for wearable tech. And finally, remember, this isn't some obscure science fiction. Its applications are all around us, right now, and they're growing every single day.
Which kind of leads to a final thought I want to leave you with. We know smart floors can harvest energy from footsteps today. As these flexible materials like PVDF get better and cheaper and more advanced, what if the shirt you're wearing could one day harvest energy just from your movements and charge your phone? The science of squeezing is really just getting started. Thanks for tuning in.